Hey everybody, thanks so much for joining us today. We have a really cool topic to share with you, and I would love to introduce Thom Lane, who's going to talk about the Keras-MXNet topic that we have today. So Thom, why don't you go ahead and take it away? We will have more attendees join here in the next couple minutes. It usually starts ramping up right about now.
All right, thanks for the quick introduction there. Yeah, so my name is Thom Lane, and I work as a machine learning scientist at AWS. Specifically, I've been working with the MXNet deep learning framework and work with both internal and external customers to help them use MXNet. And I've helped a few customers use Keras-MXNet, and that's the topic of our conversation today. So some of you may be familiar with Keras already. So Keras is a really user-friendly Python package for deep learning. And so deep learning, that's got a whole host of different applications. So we've got natural language processing is a really important component. And so just an example of that is for question answering. This is just one thing we can do of many different things in NLP. So if you've given a body of text and you have a question, then you can identify the section of the text that answers that question the best. We've also got computer vision as a whole new section as well. And so this is an example of instance segmentation. So we take in an image and then we're trying to identify different objects and the regions around each. And then lastly, reinforcement learning is another area. So it's got a lot of traction recently, especially deep reinforcement learning. And we can use Keras for reinforcement learning to create a network that can decide the best actions to take. And so, yeah, as I mentioned before, it's a really user-friendly API. So we have, this is just going to take an example of a really simple neural network. And it's got a few different layers. So these are just fully connected layers. And with Keras, really easy to do. So we're just going to look at the Python code for creating this network. We've got a few different imports that we need to do. So we're going to create a sequential network because we've got lots of layers stacked on top of each other. And then each of the layers is what's called a dense layer. And so to create this fully connected network, we start by creating the sequential block, and then we add a number of dense layers, each with different number of units. We've got 3 units, followed by another layer with 3 units, and finally the output layer has 2. And then we can apply different activations. So this is a really typical neural network. You're not going to be able to apply this network to the examples we saw previously, but this is just showing you for the most simple case what we can do with Keras. And then the final steps for training a network, firstly, we've got the compile stage, and that's just going to build the graph of all these operators. And then lastly, we apply a fit function. So this is similar to what you find with scikit-learn, for example. And we have the input data is X-train, and then the labels are Y-train, and then we run this for 5 epochs. So we pass through this data set 5 times. And there we go. With Keras, we've already trained our first neural network. And so today's presentation, we're talking about Keras-MXNet. And so what exactly is this? So in the last code example, we're working with a front-end language, a front-end Python package, which is called Keras. But then under the hood, all the operations are being performed on a back-end. And so this is where you have the optimized operations. And so when Keras started, one of the most common backends was Theano, but it's no longer being developed. And so the typical default most people are using with Keras right now is TensorFlow. But if we actually transition the backend to MXNet, there's a number of key advantages. And so they're the kind of things that I want to run through with you today. And this presentation is going to be broken into 2 sections. So the first section is model training, and then we'll be looking at deployment. So the key benefits when it comes to model training of using the MXNet backend for Keras is firstly, it really speeds up training significantly. and I'll show you some benchmarks of how much the speed improvement we can get from that. Really good scaling characteristics as well. If you want to speed up your training even more, you can use multiple GPUs to do this in multiple instances. And then really, really easy to get started. So I'll show you some installation steps here. We have a number of tools on AWS where Keras-MXNet is pre-installed, so you don't need to even do this yourself. And then for deployment, we'll look at how to deploy with Amazon SageMaker. We've also got a number of inference APIs for MXNet. And lastly, we'll look at a few different open source packages that are separate from MXNet, but one is dedicated specifically to serving models. So it's the MXNet model server. And by using MXNet, we unlock a whole host of different tools in the MXNet ecosystem for Keras. So now let's take a look at the training. I mentioned really easy to get started. So with AWS, typically you could either be using EC2 instances. There is a DLARMI, so a deep learning AMI image that you can start for EC2, and it has a number of things pre-installed. So it's got a whole host of deep learning frameworks, including MXNet, TensorFlow, and PyTorch. And it also has the CUDA libraries installed, which are generally quite difficult to set up yourself. But if you set up a GPU instance, you'll have all that ready for you, ready to go. And then another alternative is to use Amazon SageMaker. So here you have the likes of notebook instances. And a similar thing, you have a number of environments, Conda environments that have been set up for you with all the deep learning packages. And for Keras-MXNet, we want to be using the MXNet Conda environment. And we can activate this on the EC2 instance or SageMaker instance by activating it with source activate MXNet-P36. And that's just noting that we want to be using Python 3.6 with MXNet. And now when we start and run Python and import Keras, so this is as you would do normally, it's going to by default use the MXNet backend. So there's been some configuration that's done when you've activated the environment to make sure Keras uses MXNet. And it's as simple as that if you're using DLARMIs or SageMaker. But if you've got the case where you're running your own machine, maybe you want to try this out on your laptop, you can go through the install steps yourself, but it's relatively easy. So the first thing we need to do is install MXNet, because that's the backend engine. We can do that with pip install. And then there's two variants that I'd recommend looking into. So we can optimize this install a little bit more. If you're running an Intel CPU, then there's a package called MKL that will optimize. So you just change the pip install slightly. And then if you've got a NVIDIA GPU, you can use that to the full potential by pip installing MXNet-CU92. And the number here denotes the version of CUDA that you've got installed. So if you're running a different version of CUDA, you need to change that slightly. And that was the backend installed. Now you want Keras-MXNet. So again, we can just go through a pip install Keras-MXNet, and that will get everything configured for you. There's a lot more details on the MXNet website for more bespoke installations if you want to build from source, for example, but you don't typically need to do that. You can just pip install. And so once you pip install Keras-MXNet, everything gets set up, and there's one really important file for Keras. It's a configuration file. After we've done the install, this is what the default would look like. The key thing to note here is the backend parameter has been set to MXNet. So when we import Keras, we're going to use the MXNet backend. And essentially that's all we need to do. So if you've got previous Keras code that you've written and you want to try out the MXNet version, just follow those, either source activate the MXNet environment or pip install Keras-MXNet, and then you can run your Keras code and just give things a try and see how much it improves your performance. I just want to flag one potential issue that you may come across. So it's in terms of the operators that are supported. So the vast majority of operators are supported by Keras-MXNet. So there's the likes of the convolutional operators, recurrent operators, LSTMs, and a number of sparse operators. But occasionally you may find an operator, these are more of the niche operators, that aren't fully supported right now. things like conv LSTMs and the map function. And typically, if you've written Keras code and you've used the backend functions quite a lot, so if you're using Keras with TensorFlow and you've used TensorFlow operations, when you switch to Keras-MXNet, that's not necessarily going to work. But there's more often than not workarounds with MXNet equivalents, but that may mean that you can't just pip install. But for vast majority of cases, this is possible. And then there's an issue tracking the current limited supported operators with potential workarounds. I mentioned you get a huge speed up in training performance. And one of the standard ways to measure this is on the ImageNet classification challenge. So this is a data set of 1 million images across 1,000 classes, and you have to classify each of those images to a given class. And one of the most common networks, neural networks to use for this problem is a ResNet 50. And if we look at the performance statistics with Keras with TensorFlow on a GPU compared to Keras with MXNet on GPU, you can see we get a huge increase in performance. So we're looking here at the seconds it takes to process 1,000 images. And we've gone down from just under 20 seconds to around about 7 seconds with Keras-MXNet, just by switching. It would be the same Keras code for these two cases. Just to note here, we're using one GPU on a P3 8x large. We could just have a P3 2x large because that has one GPU, but this hardware was used, and we'll see a bit later on, for multiple GPU benchmarking. And another benefit of Keras-MXNet, in addition to the speed up, is the fact that it's more memory efficient. So TensorFlow typically takes the whole memory allocation of your GPU, and MXNet's default is to take only the slice that it needs. But you can also fit bigger batch sizes in memory for Keras-MXNet, which then further improves training. But for the benchmarks you're seeing here, we use the fixed batch size of 32. It's a similar thing on other benchmarks. So that was for GPU, and now this case for CPU. Slightly different data set here. So we're working with smaller images, it's called CFAR10. But again, same concept of image classification, and we see an improvement with Keras-MXNet. But it's not just on convolutional networks that we see this increase. So also for NLP, you might be using LSTMs. With GPU, we see a significant improvement with Keras-MXNet, and this is for text generation challenge. But there are some cases where Keras-MXNet could potentially be slower. This is usually limited to running LSTM networks on training LSTM networks on CPU. It's just two operators that are currently being worked on to improve that performance. But the vast majority of training typically takes place on GPU, so this isn't a huge issue for training. And then because we're using MXNet, we can make use of all the tooling provided for training on MXNet typically. And one of the useful tools, this is more for advanced users, is the MXNet profiler. And so some of you may have profiled your code previously, and this is a deep learning equivalent to profiling your code. You can start the profiler in a number of ways, but one of the simplest ways is just to set an environment variable before you run your code. Here we're just setting auto start to 1 and then run your script as you normally would. And when your script completes, you usually get an extra file, which is called profile.json. And inside this file is all the information about how long each of the operators has taken and how everything fits together on a timeline. And the format of this file is in the same format that Chrome uses for its internal tracing. So you can open up Chrome, go to the tracing tool, and then open this file, and you get a really nice user interface, which shows you a timeline of all the operators. And so just in the background, you can see a caption, or a screenshot, sorry, of one potential operator. So here we're seeing a convolution followed by a batch norm and then an activation. That's a typical block you see in lots of neural networks. We can see the convolution is taking the longest out of the operators. But this is a really good way of identifying potential bottlenecks. So it could be in data loading, or it could be in model training, the forward or the backward pass. It's just really good for the advanced users. Now, this is a really important point to make about model performance on training. The default with Keras is to use something called channel last. And you may have noticed that in the config file that was specified. What that means is if we have a number of images, they're going to be stored in an array in a certain order. So let's take the case where we have 100 color images, and the height and width of these images is 32 pixels by 32 pixels. And so the default array will save this in NHWC format. These are common abbreviations, but what it stands for is the N is for the number or the batch size. We have 100. H and W are height and width, so we see 32. And then C is the channel. So we're working with color images, which typically we have a red, green, and blue channels, which are 3. And so the data shape will be 100 by 32 by 32 by 3. But this isn't the most efficient way of storing our data. So especially for NVIDIA GPUs, it's much more efficient to have what's called channel first. It's not quite the first because we have the batch size first. We have NCHW this time. And so we just move that channel axis a little bit further up. And the operators on the NVIDIA GPUs are much more optimized for this. And so we can improve training performance substantially. So I said this wasn't the default for Keras-MXNet, but if you're using SageMaker or the DL Army, when you activate the environment that you need, it will actually default to channel first. So you don't need to do anything. So it's only the case where you've installed Keras-MXNet yourself, so this could be on your laptop, that you need to go into the config file and just change that from channel last to channel first. And then you're going to be able to make use of all these improved operators. It is possible as well to change this option from inside the code. You don't need to do it through the config file. So if you import the backend for Keras, you can then set the data format to channel first, and that's just an alternative way to do it. And we've changed how the operators are going to be processed, but the next thing we need to do is convert our data to that format. It may already be in the format, but if you've got it in the NHWC format with the channel last, there's a utility just to change the axis to get it to the channel first. As you can see that at the top line. And then the only other change we need to make is typically the first layer in your network where you provide the input shape. For channel last, the input shape of this convolution would have the 3 at the end, but now we have channel first, we've moved the 3 at the start. And with those two changes, we can see the improved performance. Now for scaling, we see really good scaling characteristics across multiple GPUs. So we've already seen the case of ImageNet training on a ResNet 50 on one GPU. But then we see a similar thing for 4 GPUs and 8 GPUs, where Keras-MXNet is much quicker than Keras TensorFlow for these cases. We go from around about 7 seconds per 1,000 images for 1 GPU down to under 2 seconds. So it's good scaling with 8 GPUs. And if we've got faster training, that just means we can iterate much quicker, we can run more experiments and get to a better model ultimately. In the code, we just need to add one extra line. It's as simple as that. There's a utility again called multi-GPU model, where we provide the existing model, specify the number of GPUs to use, and then we can compile the model after that as normal. You want to choose the number of GPUs that the machine has and no more, otherwise you will get errors. One other tool in the MXNet ecosystem that's really useful for training is something called MXBoard. So separate from the MXNet project, but it's an open source project. And this is an integration for TensorBoard. So some of you may have used TensorBoard before. A really great way to visualize all those metrics. MXBoard is a Python package to save MXNet data in a format that can be read by TensorBoard. So in this case, we're just writing data in histogram format. We import MXBoard, and specifically the summary writer, and then we add histogram on that summary writer with, it could be loss data, for example, and look at the distribution of the loss while we're training. And to use this with Keras-MXNet, there's something called a callback, which is a function that's called at certain points in your training. You could have a callback at the end of an epoch, for example, that would then call the summary writer and save the loss distributions. And then the final step of training is for the model export. So after we've done our training with the fit function, we can then go Keras models and save MXNet model. And the two things that we specify here are firstly the train model, and secondly a prefix. It's just kind of it gets added to the start of the model files. And so after we run that function, we'll have created two files. So the first one is a symbol.json file, and that describes the architecture of the network, so which operations are performed in different orders. And then there's parameters file. So inside the network, there's a number of parameters that are learnt, and the params file contains all that information. So let's just have a quick code walkthrough of doing this on a SageMaker notebook. And we're going to run Keras-MXNet code to train a convolutional neural network, just on a really simple case. I'm just going to escape the presentation for a second. Okay, so we've moved across to, and this is a SageMaker notebook. Just like Jupyter, so we have Jupyter notebooks that we can run, and each notebook is running in a certain environment. So I've activated the MXNet environment. And so my configuration file for Keras has been set with channel first, which is, as I mentioned, is the more optimal choice. We have a number of imports here. So we have, we're going to use the data set MNIST, and so that's just handwriting recognition. And then the layers, so we're going to be using convolutional networks, so we import layers such as conv2D. It's going to do two-dimensional convolution. And then, as mentioned, we have a number of utils. So here, to channel first, because we're going to switch the dimensions of our data. We can create the data set. This is just because it's a pre-baked data set for Keras. We can just load the data. We have the training split and the test split. We want to train on the training data. But if we look at the shapes of the data, we have 60,000 images, 28 by 28 height and width. But there's no channel because it's a grayscale image. So we haven't got 3 in this case because it's not a color image. But to use the convolutions in the most optimal way, we do need to add this channel axis. We're dealing with NumPy arrays, so we can just do it in a typical NumPy fashion of adding a new axis. But then we need to make sure that this channel is added channel first. So we want the 1 before the height and the width rather than at the end. And so that's why I'm calling to channel first to be able to do this. So now we have the data in the right format. We can do things such as normalize the data because we're working with neural networks. We want to have our data standardized. So we're just going to convert to floats and then divide by 255 because that's the typical maximum for images. So now we have our data in the range between 0 and 1 for all those channels. Our Y variables, this is the label. What we're trying to do is predict the class of a handwritten digit between 0 and 9. And so we one-hot encode those class variables, which we call two-categorical. Then the model, we're going to be working with convolutional network. So we create a sequential network and add convolutional layers with different kernel sizes and filter sizes. The next part is to compile the network. We're going to train this using the Adam optimizer and use categorical cross-entropy loss, which is used for categorical variables. And then we fit our model with the data. We're going to run this for 5 epochs, and then we get the logs of our training. So each step took in the order of about 3 seconds, really, really quick, because we're working on a GPU with a tiny data set. And because Keras-MXNet is quite quick as well. Run a quick evaluation on this model. We see the accuracy is very high. We're at 99%. And the last step would be to save the model. So we're using the save model function with a prefix of mnist_cnn. And then we can see we have the 2 files that have been saved, as mentioned. We also get some useful information for deployment. So the first point is something called data names. And we're going to use this later, and that's going to tell us which part of our graph is used for the input. And then we can see what the output is. And for that input, it also tells us what shape the data should be. So this is all going to be useful later, and I'll show you when. Okay, so let's hop back to the presentation. So we're looking at now model deployment. Typically, the model training will be done by a scientist, but when it comes to model deployment, there's a number of other components we need to think about. So we've got engineering, and we've got operations as well. So you may, in your company, have different teams working on each of these aspects. But if you're just a scientist and you want to have some of these deployment options supported for you, there are tools within AWS to help you on the engineering and operations side, just to be able to deploy the models. But we'll see cases if your company has an engineering team, operations team, we'll have tools that fit with those as well. And when it comes to model serving, there's a number of areas where we have undifferentiated heavy lifting that AWS is going to do for you. So when it comes to training your model, that's really where you can differentiate in terms of the performance of your model and what the model is doing. But there are certain areas that we always want to have good performance, good availability, and good networking. Monitoring tools are really important as well to be able to see how the model is scaling, to see whether we need to increase resources or not. And then we want to be agnostic to a number of different things, such as the model itself. We don't want to reinvent the wheel for just a slightly different variant of a model. We want this to work across frameworks, not just for TensorFlow, MXNet, or PyTorch, for example. And we want to be able to work cross-platform so that we could look at deployments on the cloud, and we could also look for deployments on edge. And SageMaker is a really good way to go for the whole ML pipeline. So we have tools starting with labeling your data. We've got SageMaker Ground Truth for doing active learning and labeling in the most efficient way. As we saw before, we had the notebooks for building your neural network models and then doing the training, which we can do on the notebooks or in SageMaker mode and Docker containers. Then we have the tuner for automatic model tuning. But the areas that I'm going to focus on today are around compiling the model and optimizing that, and then deploying on either the cloud or edge. So for edge deployments, we're going to look at something called Greengrass. And Amazon SageMaker Neo is a model compiler that will take those model files that we exported in the previous step and then compile it specifically for a type of hardware. So we can choose between Intel, so if we're running on the cloud on an Intel optimized device, we can optimize for this. If we have a GPU, we can do the same for NVIDIA. But if we're looking at edge deployments, or maybe it's better if we target devices such as ARM and Qualcomm, and we can do this with SageMaker Neo. And why do we want to optimize? Well, again, it speeds up inference this time. We looked at speeds up for training, but if we're using Neo, this is for inference purposes. This is a case for ImageNet, image classification again, same network on CPU. And we can see before and after using SageMaker Neo, we get a huge improvement in the latency. This is for a batch size of 1, so we're just passing a single sample through the network. And we've gone from 180 milliseconds down to 20 milliseconds. And so how is this possible? So I just want to run quickly through a few different types of optimizations that are being applied here. They break down into 2 categories. So firstly, we've got graph optimizations and then tensor optimizations. And some of the most simple graph optimizations are, let's say we've got a number of operators in a row. So this is what the computational graph might look like: convolution, activation, and then dropout. But for inference purposes, we don't need some of these operators. So the likes of dropout, we can actually remove directly for inference, which will improve performance. We don't need to check whether we're training or in inference. And then we can combine operators together. So if we have a convolution and an activation applied one after another, we don't need to store the intermediate results between these two. We can apply them both at the same time, which will save time allocating memory and things like that. And this is called fusing. And then if we look at the individual operators, so we saw how changing the channel order to channel first had a huge improvement in speed. Or we can actually do similar things, but at changing the number that we've got in each of these dimensions. So this is called tiling, where you just have a tiling factor to shift data. And this uses the cache in a more optimal way. But this is all done for you. You don't need to know exactly how to be doing these operations. And then lastly, vectorization is, instead of having a for loop through your data, through different arrays, for example, we can just apply a single operator on 2 different arrays together, which is much more quicker in terms of processing time. So that was the compile stage. It's totally optional to compile your model. You don't need to do it, but if you do, you get a huge improvement in performance. And then we can do this for cloud deployment and edge deployment. So let's take a look now at cloud deployment using SageMaker. And we can do this using the SageMaker Python SDK. And these are kind of the main components that you'll see with SageMaker code. So the first thing you create is something called an estimator. And an estimator, you then fit a model with training data. You can perform this in the notebook directly, but more often than not, you want to do the training in a dedicated training environment. And SageMaker creates this environment for you using Docker containers, where you can run training much more efficiently. So now you have your train model after calling fit, and the train model is stored in S3. Then when it comes to deployment, you can take your estimator and call .deploy. And this will convert your estimator into something called a predictor, which is ready to make inference calls. And when we want to make a prediction, we call the .predict function on the predictor. And this is going to run the model that was saved in S3 in the prediction environment. And again, this is typically in Docker containers. You don't have to call .predict through SageMaker, because an endpoint is created. You could use typical REST API clients and services. You could use curl from the command line, for example. Or you could do this through your browser. And in the last diagram, when we had the estimator, so just here we have a script.py. So inside the script is going to be your training scripts, but also some inference code. And so the key components for cloud deployment, there are defaults that are specified for all these functions, but you need to specify 2 ones in particular are important. So we've got the model function, and this just tells SageMaker how to load your model. So we are saving an MXNet model, so we can use the symbol block from Gluon. This is pretty standard. You can take this as is for most cases. And then we pass in a few different parameters. So we have the two files that were exported by Keras-MXNet. We have the architecture file and the parameters file. And then we also specify the input node, which was printed out when we did the save model from Keras-MXNet. And that's all we need to do. So now we have a network in MXNet. There's also an input function. If you don't define it, it uses a default. This just parses the input request. So we have a JSON input, usually from the endpoint, that contains our data that we want to do the prediction on. This could be an image, for example. But the input function by default will process this for you. And then after that, it will call the predict function. And predict is just going to apply the model to the input data. So here we provided an input that didn't have the batch dimension, and this is just creating a batch of one, and then we pass this batch with one sample through the model to get our prediction. And then the output function will be called at the end, but again, if you don't specify this, a default will be used. And this just serializes the output prediction, and it means we can pass it through the endpoint and get our prediction. And then the last thing we just want to touch on for SageMaker is the edge deployment. So we've got really good integration with a tool called AWS IoT Greengrass. And Greengrass is a good service for managing edge devices or collections of edge devices, where once you've done your training on the cloud, you can then define something called a Greengrass group. And inside the group, you have a number of devices. You designate one of these devices as your core, and this is the thing that's going to interact with the cloud. So once you've trained your neural network model and you've exported it, you can deploy this as a resource to the core, and then the core can use this model as part of a Lambda function to interact with the devices. So you may have a camera in one of these devices, which will interact with the core. It will run the neural network model on the device on edge without ever having to go back to the cloud. And then in turn, you could maybe run object detection on that camera to then decide to control other devices. And this is all done on edge. You don't need to then interact back with the cloud. But when you need to, for updates and things like that and model deployments, with Greengrass, the whole connection is secured and works with shadowing when the devices go offline. And so now let's have a quick walkthrough of some code of deployment. Just want to show you with Amazon SageMaker how easy this can be of the same model that we were working with before. So I mentioned there was this script.py file. A lot of this code will look familiar to what we used before for training, because I have training and inference code in the same file. These are the inference functions that we saw on the previous slide. And then we have the training from the notebook. And so this is all just in one single file. Now from another notebook, we can use the SageMaker Python SDK. So I import from SageMaker, so it's another Python package, the MXNet estimator. That's the important thing to note here. There's a little bit of setup. We need to create a session and we get a role. So role is going to manage the permissions for running these containers, the Docker containers. And now we create an MXNet estimator. We specify the script file that we're interested in that has our training and inference code. Then we choose the instance type to do our training. So here I'm using a GPU instance, P3 2x large, and specifying that I want to use MXNet 1.3 with Python version 3. And our script can take a number of parameters. So I'm using argument parsing in my keras.mnist.py. And so that it's looking for batch size and epochs. So this is really general. We can pass in whatever we need here. And this is how automatic model tuner integrates as well, by varying these hyperparameters to find the best. So we've created that estimator, and then we can go ahead and call .fit. And this is going to start the training job, load in the data, In this case, we have our data download defined in the script file, so we don't need to pass in the data. It's going to run, we've got quite a lot of logging output, but it's going to run through the training. You can see it's just as quick as before. And now we have our model saved in S3. And so for model deployment, we can simply take our estimator, call .deploy, and then choose the types of instances that we want to deploy our model on. And here, choosing a CPU instance rather than GPU. Now we get a predictor. We can go ahead and run a prediction. So I think I've tested this. We take a number, for example, and then we can call our predictor with .predict and pass in the data that we've just used. We're taking an argmax here because we want the most likely number. We get probabilities of every number, and its prediction from the model was 7, which is what we just drew. When you're finished with an endpoint, you should go ahead and delete it, just so it spins down those prediction environment. So that was all fine if you want to be working with AWS SageMaker, but maybe you have an engineering team that already has a deployment process already in a certain language. So MXNet provides a number of inference APIs. For training, you'll be using the different interfaces such as Python, R, and Julia. But then the preferred APIs for inference, we have inference APIs for C++, Scala, and Java. And in each of these, we have sort of customized deployment options for different types of neural network tasks. And these are much more optimized. So let's take Scala as an example. For object detection, maybe in Python, with SageMaker, we've trained using Keras-MXNet, an object detection model. We save the model and we get those two files, the architecture file and the params file. And now using Scala, we can create an object detector. So on line 11, we create a new instance of an object detector and we provide a path to our model with things like the input descriptor, which we got from the save model output, which shows the data format that we need for an image. So in this case, we're passing an image of 224 by 224 height and width, and it's a color image. And then we choose a image that we want to perform this object detection on. So we have the path at the very top. And lastly, in the bottom line, we call the image object detect function on our object detector. We pass in our image and we specify that we're interested in the top 3 predictions. And then the example would be on the right-hand side where we've identified, the dog, the bike, and the car. And so this is just using SageMaker API. This is using the Scala API for MXNet to be running inference. Another great open source tool, so this is a separate open source project, is the MXNet model server. And this just provides a lot of functionality that's typical for model serving. So it will create a web server dedicated for doing model inference with MXNet models. But it's not just MXNet models that you can work with. It also supports the Open Neural Network exchange format, ONNX, and we can load in ONNX models through here. And the core component of MX Model Server, to make it agnostic to different types of model and framework, is to create something called a model archive. And then when we have a model archive, we can then deploy that on our server, and we can create an MXNet model server using this archive. So let's take an example of creating an image classification endpoint. And we're going to use a network called SqueezeNet in this case. So once we've trained our SqueezeNet model, we have the architecture file with the parameters file, but there's a few other things that we need for the archive. Firstly, it's a Python file that's just going to control how we pre-process our input and obtain the data in the right format for the model. And then something called the signature.json file, and that just specifies the data format itself from the endpoint. We can combine all this into an archive using the model archiver command, specifying the paths, the models, and the handler, which is the Python file that's going to be run first. And then when we have our .mar, the model archive file, we can start an MXNet model server with the MXNet model server command and specify which model archive we want to use. And after you've run this command, so you might be running this on an EC2 instance, for example, it's going to start the web server, and then we can make REST API calls. So it's going to create an endpoint by default at /predictions/SqueezeNet, because that was what our model was called. And we can pass an image, in this case, to that endpoint and get back our predictions. And here we've got the classes of this particular image. The recommended approach for working with MMS is to use something called AWS Fargate. It's just a really nice way to manage specific tasks. So here, similar to Elastic Container Service, where you specify a task that you want to run, but with Fargate, you don't need to specify the instances that are going to be used to run your model. You just specify the requirements for your task in terms of CPU and memory, and then AWS Fargate will manage what instances to use and scale up efficiently. So in summary, we looked at model training. We saw how Keras-MXNet speeds up training substantially, can be used for multiple GPUs, and is really easy to get started. And then for model deployment, we looked at SageMaker, looked at the MXNet inference APIs, and lastly, MXNet model server. So thanks everyone for joining today. And then, yeah, happy to take some questions. Have a look through chat.